Decarbonization, Energy and Environmental Equity Platform Research. I'm Stephanie Waldoff, an earth scientist at PNNL's Joint Global Change Research Institute. In the first 3 deep dive webinars, we've seen in detail how decarbonization policy is being modeled in GODEEEP and the results of that research and analysis. In today's deep dive, we'll be looking at the effects of those ambitious policies on and how they will impact consumers' energy and environmental equity, focusing on the distributional impacts on different groups at multiple spatial and socioeconomic resolutions. Today, we'll be hearing from 4 of our researchers, Brian O'Neill, Ying Zhang, Sumitra Ganguly, and Stefan Rose. Brian O'Neill is an earth scientist and laboratory fellow at PNNL's Joint Global Change Research Institute. His research interests are in human-earth system interactions, in particular the human dimensions of global environmental change. He holds a PhD in Earth System Science from New York University, and previously he was a professor of international studies at the University of Denver and a senior scientist at the National Center for Atmospheric Research. Ying Zhang is an earth scientist in PNNL's Joint Global Change Research Institute. Her interests include integrated human-earth system modeling, policy and climate change impacts on food and energy water systems. She holds a PhD in civil and environmental engineering from the University of Wisconsin-Madison. Prior to joining the lab, she was a postdoc at Johns Hopkins University. Sumitra Ganguly is an economist with PNNL's Electricity, Infrastructure, and Buildings Division, where she uses her skills in quantitative economics to answer various energy policy questions. She holds a PhD in monetary economics from the University of Missouri-Columbia. And prior to joining the lab, she was working as an adjunct professor at the University of Maryland, Baltimore. Stefan Rose is a geospatial data scientist in the Earth Systems Predictability and Resiliency Group at PNNL. He's the lead developer of the Energy Justice Visualization and Impact Analysis tool for GODEEEP. He has previous work experience in energy consulting, evaluating utility programs focused on renewable energy access and equity within disadvantaged communities. He holds a master's degree in geography from Oregon State University. I want to note that we'll have a short question and answer after each presentation and an open Q&A at the end. We have over 100 people registered today, so I'm really looking forward to a great discussion. Please put any questions in the chat and the panelists will see them. I'll read the questions and the panelists will answer. Next slide. Before turning this over to our speakers, I want to first present the motivation for this research and give a roadmap for what we're going to hear about today. Our first 3 deep dives focused on the impacts of net zero energy transitions to the energy system and electric grid. These changes will also have profound effects on the people who use energy and those whose jobs are in the energy sector. In today's webinar, we'll focus on this component. Our presenters will explain how this research can inform policy-relevant questions focused on energy and economic security. How will consumers' energy security be impacted by a transition to a net zero emissions economy? What types of jobs are going to be created or lost, and where will those jobs be located? What are the implications for consumers' incomes? And in particular, how will disadvantaged communities be impacted? We'll show how these questions, which occur across multiple spatial, temporal, and socioeconomic resolutions, are being answered within GODEEEP in a fully consistent framework across all these scales and metrics. We'll also demonstrate our EJ-VIA tool that enables stakeholders to interact with these results across a range of scenarios. Next slide. GODEEEP is a novel framework that looks at all the components of the system, from state-level capacity expansion needs within the context of US and global decarbonization policies and a changing climate, to hourly load projections and renewable time series profiles, infrastructure expansion and renewable electricity availability, power grid operations, and the impacts on environmental and energy equity and justice. Our platform is designed to be fully consistent at every single stage of this analysis. Next slide. Today, we'll be focusing on how the effects of net zero emissions policies impact energy and economic security across a range of scales, both spatial and socioeconomic. Next slide. We'll show how we use our models to explore state, county, and census block scale impacts. Next slide. We've developed multiple metrics of energy and economic security at a range of spatial and socioeconomic scales. We'll show how GODEEEP can be used to quantify impacts of decarbonization on residential energy security for different income deciles at the state level, changes in jobs and income at resolutions as fine as the census block level, and disadvantaged community status, specifically how these changes can move a community into or out of DAC status. Next slide. We'll also see how we've developed the necessary inputs for these analyses, specifically consistent projections of state level income distribution and census block projections of population and income. Next slide. Our presentations today will describe both the outcomes and the modeling that goes into producing these outcomes. Next slide. We'll also be sharing our new tool for decision makers to analyze and visualize the implications of policy actions in this full range of energy and economic security metrics. Next slide. Brian will be sharing our work on socioeconomic projections. Ying will talk about work on residential energy security. Shamitra will review our work on jobs, income, and DAC status. Stefan will explain and demonstrate our EJVIA tool. And now I'll turn it over to Brian.
All right. Thanks, Stephanie. So I'll be talking about how we generated some important socioeconomic information on future income distribution that's then used in the rest of the project, both for analysis of outcomes at the state level across the US, as well as for more highly resolved analysis at the census block level just within the state of Washington. So in this wiring diagram that Stephanie presented of the overall project, I'm talking about these two orange boxes at the top on income. And the rationale for doing this in the first place is that, as Stephanie said, we're interested in modeling impacts on different groups of people because they can be affected differently by the energy transition. So to do that, we need to actually differentiate types of people within the models. And we need to project the number of people in these differentiated conditions into the future because they're not static. They're going to be changing at the same time the energy system is changing. Now, if we look at the next slide, there are a number of dimensions of such heterogeneity or kinds of differences among groups of people that we might want to consider in principle: age, sex, urban, rural residents, race or ethnicity, income, education, so on. For this work, if you just forward the animation, we decided to focus on one of the most important distinctions, which is income, which itself is a really important indicator of vulnerability. So our overall objective for this work is to produce projections of multiple income groups then for the US states and for alternative scenarios so that we can cover uncertainty in those outcomes. And this required breaking some new ground because currently there are no such projections out there. What we do have are projections of within country distributions rather than within state, like the one I'm showing here, which is a projection of US income distribution for 2050. And the way this plot works is it divides the population up into 10 equal-sized groups on the x-axis. Those are deciles, and shows the share of national income on the y-axis. And so you can see how much different the earnings are in the highest decile, for example, on the right at nearly 40% of national income, while in the lowest decile, all the way at the left, that decile is earning maybe 1 or 2% of total income. And the method used here is typical one. It's relatively simple in that it assumes a particular shape of the distribution. That is here in particular that it's log normal. And so for our task, we need new data and improved models at the state level that don't make such simplifying assumptions. So let me describe our overall approach to this challenge and then give you a little more detail. So what we want to produce on the right of the slide here are projected income distributions for each state, right? Not just for the country as a whole, for alternative scenarios of possible outcomes and measured in different ways. To produce these, we combine three types of projections. Population projections for each state, projections of overall economic growth for each state in GDP per capita terms, and projections of how total income is distributed within each state across deciles. Now, the first two of these we take or we construct from existing sources. In particular, for example, the population projections are taken from a set we produced here for the IM3 scientific focus area. But the key task for us in this project was to develop new projections of how each state's income is allocated across the different deciles of the population. And this required a fair amount of work on data for current state distributions, which took into account federal and state taxation, which have important effects on income distribution, and also model development to be suitable for state level projections. So I'll say a little bit more about how the projections work in a minute, but first just one additional word on the alternative scenarios we use to represent uncertainty. We're drawing on widely used scenarios in the climate community called the Shared Socioeconomic Pathways, or SSPs, and they are intended to represent futures with a range of different vulnerabilities. We use three of them. One that's a kind of middle of the road scenario, and then two more that span high and low vulnerability futures. These three scenarios represent different assumptions about population growth, economic growth, and inequality. In the literature, the three that we're using are known as SSPs 2, 3, and 5. So you'll see those labels pop up in the presentation. Okay, back to a little bit more detail on our approach. So we adapted an approach for projections that we recently developed for doing national projections. And adapted it to the state level. It's a non-parametric approach, so it doesn't rely on assuming a log normal or any other distributional form. So we can, with this approach, let the data play a larger role. It's based on a principal components approach, which uses historical data to find basic shapes to all of these underlying distributions, which are here shown in the kind of mass of gray lines, that when combined with different weights to each shape can reproduce these observed distributions. And in this case, these observations are for countries at different points in time. And so we found with this approach that with just two of these shapes or components, you can very accurately reproduce distributions across all countries and over the past several decades. And as an example, the black dashed line, if you can see it in there, shows an income distribution that is predicted from the model, combining these two components, PC1 and PC2. And you can see it produces a very similar shape to the historical patterns. So to turn this model into projection model, we need to project the weights that you apply to each of these components in the future. And we find that variables such as the Gini coefficient, which is an inequality measure, the labor share of income, and some lagged variables are good predictors of these weights. So that's the way the model works. As mentioned, we also needed to put together new data sets at the state level for income distribution. This required drawing on a bunch of different data sources, not just for gross income, but also to adjust for taxes, since they strongly affect the distribution. And we use this data not just as a starting point to represent current conditions, but also to validate the model. And our validation steps have shown that the model works quite well at the state level. So let's look at just a few results. First, what do we get when we look at what is per capita income for the poorest and richest deciles of populations within states in our projections? And I'm showing this in these histograms on the left, which show how many states have income that falls within certain ranges in 2050 for our 3 alternative scenarios. On the left, you see that the income for the poorest 10% of the population varies across states and across scenarios, but it's generally in the range of $1,000 to $15,000 per person. Same thing on the right, where the richest 10% vary from around $200,000 to $400,000 per person. And on the far right, we calculated some metrics of how unequal state distributions are. For example, here I'm showing the Palma ratio, which is just the ratio between the top 10% and the bottom 40% of the population in income terms. And you see it varies across states and scenarios again, with certain states like New York, California having the highest inequality, and others like Utah and Wyoming having the least. So the data underlying these figures is, in fact, one of our key outputs for this part of the project. It's projected income distributions for each state over time for 3 different scenarios. These results, for example, are then used in the work that Ying is going to talk about next to look at state-level energy security outcomes. But in addition, we also use our results for the state of Washington in particular on the next slide as a starting point for further downscaling from the state level to the level of census blocks to support fine-scale analysis of energy transition impacts on income and jobs. So that starts with these 3 alternative scenarios for the state. As you can see, there are different amounts of income growth. The top line has higher growth. The bottom line has lower growth across all the deciles. It's harder to see the difference in inequality, but there is some that's indicated by how skewed the distribution is. So let me just explain at a very high level what was done to carry out this downscaling, which can be applied to any state, but here is done for the state of Washington. So for any given projection year, the projected decile distribution is combined with base year data for the state for 16 income bins. So our decile distribution is in that top green box on the left. The base year data is in the blue box on the bottom left. This combination is done to take advantage of the additional income information that's available from household surveys. In this case, it's the American Community Survey to make sure these 2 are consistent. So this combination converts the distributions to common units and fits a continuous distribution to the data to produce our single reconciled distribution, still at the state level. The next step is to downscale this distribution to the block level. And now to do that, we use detailed employment data that's available at the block level for the base year for 3 income bins within each block. This is called the loads data. And that's the trade-off here that we're faced with. These data are good in spatial terms because they're representative at the block level, but they have much less resolution in terms of incomes, just 3 bins of income. To downscale to these 3 bins, we assume that the geographic distribution of each bin separately remains the same in proportional terms over time. So what we end up with for each projection year, all the way on the right here in this diagram, is a projected distribution by 3 bins of income for each census block in the state. We also did some accuracy assessment using recent data to test the model and found it produces reasonable results. So let's look at those results, and we'll start with the base year. And this map shows what we're showing here as a result is the proportion of each block group that is in the lowest income bin. So each of these spatial units has a distribution, has a number of people or households in each of 3 bins. What I'm showing here is the percentage that are in the lowest bin. So the lowest income block groups have the highest proportion and are the most red in this plot. And you can see they're located in the eastern portion of the state predominantly, with some patches in the west. Now, if we go to the next slide, we see this same plot, but projected to 2035 using the SSP2 scenario. And we see overall income growth, that's indicated by the shift away from the reddish colors to the blue colors, but with a similar geographic pattern of lower income in relative terms in the east and a few patches in the west. And as mentioned before, these projections of income are then used in work on predicting job and income changes for disadvantaged communities. But before hearing about that work, I'm going to turn things over to Ying, who will talk about analysis of energy security at the state level.
Thanks, Brian. I think we have time for one or two questions. The first question is about the PCA model and what magnitude lag for labor share generally fits the best.
We used a lag of one, if I recall, one period prior of a measure of the existing inequality in a state. So we used a lagged measure of the share of income in the 9th decile, for example, and I believe the lag measure of the Palma ratio, if I recall, but a one-time step lag.
And are the income projections in 2035 in real terms? Are they corrected for inflation?
They are in real terms, yes.
There's a few more questions, but I think I will save those for our general Q&A, just so we can make sure to get through all of the presentations. Thanks, Brian, and now we can turn to Ying.
Okay. Yeah, thanks, Stephanie and Brian. So the focus of this part is to examine the distributional impacts of decarbonization policies on different consumer groups at the state level. So here we have a focus on the residential energy security. This is obviously important because consumers, especially those with lower incomes, can be significantly affected by these policies, particularly through potential increases in energy prices that may impact the affordability of the residential energy services. So to do that, to evaluate the decarbonization effects on residential energy security for different income groups across the states, we've incorporated the state level income distribution projections as presented by Brian into a model called GCAM, and we ran the model under different scenarios. So next, I'm showing the two contrasting scenarios I'm presenting today. One is the business as usual, which includes existing state level energy and emission policies. The other one is the net zero policy scenario, which goes beyond the business as usual and imposes two national targets as listed here, including the ambitious goal of net zero greenhouse gas emissions by 2050 in the US. So before we dive into results, let me introduce the metrics we used to measure the impacts of decarbonization on residential energy security. So first up, we have the energy service consumption. This basically measures how much energy service is received by consumers to meet their specific needs like heating and cooling. It gives a clear picture of the amount of energy used, as well as the mix of fuels and technology choices being used to supply that energy. And the second one, we've got the satiation gap of a specific energy service. So this one is basically a measure of human comfort. It measures how far a consumer is off from the maximum satisfaction level where the energy needs are fully satisfied and they are no longer seeking additional energy services or improvements. And last but not the least, we have the energy burden. So this one gives us an idea of how much of a household's income is spent on residential energy services. And we've got some real numbers here. So in 2020, about 27% of US households reported some sort of energy burden, according to the US EIA. So next slide, let me give you a very high level overview of the model we used, the GCAM model, which comes with the new future of multiple consumer groups in the residential energy sector. So this diagram gives you some of the basic components in the model, but I want to talk about the general concept of global integrated multi-sector model and why this kind of model is essential for understanding the decarbonization impacts. So why global? Well, first of all, because global, the world is interconnected through trade. So things like energy and agriculture products, which have a carbon footprint, can be traded internationally. So we need to capture those global trade activities to model regional decarbonization effects. And besides that, the path to decarbonization requires transition of energy supply systems and significant electrification across energy demand sectors like buildings. So the integrated multi-sector aspect allows us to capture the complexities and interdependencies of these systems and sectors. So the GCAM model, that's short for the Global Change Analysis Model. We use this model in this study. So this model is one of only a few models in the world that fall into the category of global integrated multi-sector model, also known as integrated assessment model. So GCAM is a powerful and unique tool to analyze the long-term impacts of decarbonization on both the supply and the demand side. So within GCAM, we've got GCAM USA. GCAM USA gives us a detailed look at the US energy systems at the state level. In addition, it can check multiple greenhouse gases, not just CO2 emissions, making the model essential for supporting long-term strategy focused on achieving net zero greenhouse gas emissions. So next, let's take a closer look at the building sector in GCAM USA, because the residential energy security is our main focus here. So within GCAM USA, the building sector is split into residential and commercial. And under the residential sector, it models 14 different energy services like heating, cooling, hot water, and other essential services. So the model uses a nested structure based on logic choice to represent fuel and technology computations for each energy service. So each service starts with a mix of fuels, and then under each fuel, there are different technology choices, typically with one standard efficiency technology and other high efficiency technology. So the future of residential energy use is shaped by a few factors. First of all, the changes in floor space demand. So basically how much residential space people need. This will depend on the income and population density. And then there is the service demand per unit of floor space, which depends on factors like climate, building characteristics, and the affordability of energy services. So consumers with different income levels would have different affordability levels given the energy prices. So they would respond differently in energy demand and their technology choices for that energy. So finally, let's take a look at the results. So this is using the income distribution projection under SSP2. So first, we're looking at the level of heating service received by different consumer groups under the two scenarios, the BAU and then the net zero. So here I'm using the Washington state as an example. As we see, the lowest income group, D1, has the lowest consumption in heating service. But what's interesting here is that the technology choices vary among income groups. The lower income group relies more on traditional wood furnaces for heating. So those are the blue bars you see in the figure. And it's also less electrified compared to the higher income groups. And if we are looking at the net zero minus the BAU results, which is the right column of the figures, for the high and middle income groups, the net zero policy leads to a shift in heating service consumption. They're basically moving away from mostly natural gas fueled equipment and switching to electric heat pumps, which are more efficient and use electricity. So for the lowest income group, this is a different story. So as we see here under the net zero, their heating service consumption using electric and natural gas equipment decreases compared to the business as usual, this is likely because energy price increase, making it less affordable for D1, especially when it comes to these more expensive fuels and technologies. As a result, the lowest income group D1 decreases their consumption of heating service under the net zero, leading to a higher satiation gap, which we'll take a closer look on the next few slides. So here we're looking at the satiation gap for residential heating service using modern fuels. We're focusing on 3 consumer groups here under the business as usual for 2020 and then 2045. Again, higher gaps indicate lower comfort levels. To make it easier to understand, we've defined the comfort levels based on the satiation gaps as shown here in the map legend. It gives us a good sense of where the US population stands. So it turns out that the lowest income group has the highest satiation gap on average when it comes to modern heating services. In 2020, the lowest income groups in all states fall into the low comfort category, and this doesn't change in 2045. For the middle income group, some states fall into the high comfort category while others don't. This is due to factors like climate. So states with warmer climates like Florida may not need as much heating as the other colder states. And of course, income levels also play a role. So D1's income can vary across states. So income level of D1 in one state may be higher than the income level of D1 in another state, leading to different affordability of the energy service. So next, we'll take a look at the actual value of the satiation gap so that we can see the very detailed changes under the impacts of the net zero policy in 2045. So here we see that under the BAU, the first row of figures that shows the D1 satiation gap is way higher compared to D5 and D10. And now the net zero minus business as usual results are shown in the second row. Here, D1 stands out as the most vulnerable group, basically, experiencing the highest increase in its satiation gap under the net zero policy scenario. That's something policymakers may want to pay close attention to when it comes to designing equitable policies. So let's move on to the next slide. Here, we're looking at the energy burden under business as usual in 2020 and 2045. We categorize the energy burden into high and low here using a threshold of 4.23% defined based on the USEIA report. So D1 in all states is under the low energy burden category as we would expect. However, the middle income group, it's under the high energy burden category in more states than D1. This is mainly because D1's consumption levels are extremely low, as we just saw, leading to a lower energy burden, but a much larger satiation gap than D5, as we've seen earlier. Looking into the future in 2045, the projected energy burden is generally lower than in 2020. That's due to the increased affordability of all services, along with an anticipated increase in income. So next, let's look at the impacts of net zero policy on energy burden in actual values. So as seen here, in the second row of the figures where it shows the results of net zero policy minus business as usual results, it is very interesting that the middle income group could be more affected by the net zero policy than the lowest income group in terms of energy burden. So again, this is because D1 has relatively low energy consumption levels under the business as usual. That means the energy burden is less responsive to price changes when we switch to the net zero policy scenario for D1. Although there are some decreases in energy consumption under the net zero scenario, it only offsets a very small fraction of the price-induced increases in energy burden. In addition, on the next slide, we also looked at how the net zero policy scenario affects existing disparities in energy services among income groups. To measure this, we use the Palmer ratio. So this is basically the service of the highest income group divided by the sum of service of the lowest four income groups. This is usually used to measure income inequality, but here we're using it to measure the residential heating service inequality. A higher ratio means there's more inequality in heating services. So as we see under the net zero scenario in 2045, several states show higher heating service inequality while others don't seem to be affected. The spatial variability is due to multiple factors, including the different income distributions across states. And on top of that, the current state level energy and emission policies also vary across different states. So to sum it up, our research quantifies the impacts of decarbonization policies on residential energy security across different income groups and states. We see that despite the influence of decarbonization, income disparity still plays a big role in shaping residential energy security. In addition, the impacts of decarbonization can differ across different income groups, and in some states, they can exacerbate existing disparities in energy services among these groups. So I hope this gives you some valuable insights into how decarbonization impacts consumers, and for policymakers, this research can help make informed decisions when it comes to designing equitable decarbonization policies. Thank you, that's all I have.
Thank you, Ying. I think we have time for one question now, but please go ahead and put more questions in the chat because we can take them at the end as well. The first question for you, Ying, is what are the main factors contributing to the spatial variabilities in the residential energy security metrics across different states?
Yeah, so that's a good question. So first of all, the income distribution, like I mentioned, it's different across states. So, so for example, D1's income level in one state could be higher than D1's level in another state. And also the disparities of income beings are different. And also the state level policy could be different across states. Those are represented in the business as usual scenario. So if a state is already very aggressive in its emission policies, and then maybe the net zero policy scenario won't have as much as an impact as other states. And another important factor is the climate. So depending on the energy services we're looking at for heating service, states with colder climate could have higher need for the heating services. So that could be causing the state variability as well.
Thank you, Ying. Now we can turn it over to Stefan.
Okay, thank you, Stephanie. Hi, everyone. Good morning or good afternoon. I want to talk a little bit about the GODEEEP results visualization and analysis platform and the need for such a platform. So you may have attended some of our other deep dive presentations, or indeed our very first overview webinar of the GODEEEP project. But even if you didn't, or even if you did, here's a nice refresher of some of the important components and the inputs within the project. We start with the climate, the future climate scenarios, which come from the shared socioeconomic pathways you've heard us talk about earlier in this presentation. We then take the decarbonization scenarios, which are adapting using the GCAM USA model, also discussed extensively within our first deep dive and earlier in this presentation. And we then utilize the grid network topology, or the on-the-ground network of generators, transmission lines, and substations that feed into an hourly grid response using our electricity demand model and operations. And these help us generate highly practical outputs such as unserved energy loads, mean locational marginal prices of energy, interconnection costs, and emissions change. We then can generate power plant sightings that take into consideration many constraints and exclusion areas, such as protected lands, zoning, and insufficient infrastructure. And finally, we reach some of the data sets and products we have discussed here today, including changes in jobs, income, and state level residential energy security. And these are all components and the inputs within our equity impacts model, a visualization and analysis tool that allows users such as yourselves to navigate the sheer breadth of outputs we have created in this project. And specifically, this platform is called an Energy Justice Visualization Impact Analysis, or EJVIA. This platform is a geospatial analysis tool that will be available starting in September up on our GODEEEP project website that allows users to select the metrics and aggregation scales such as state, county, census tract, or block, and decarbonization scenario and the disadvantaged community definition, and explore the spatial relationships within these different energy futures and metrics. And the platform also allows users to filter and download the data outputs based on their preferences and inputs. And here I just want to reiterate how these data models and components have fed into and created the metric that are currently being developed into the tool. So these metrics include emissions and the change in emissions we forecast aggregated from the generator or the plant scale, as well as outage hours and unserved energy loads. We also are continuously looking for feedback on the types of metrics or analysis that would be most useful to our end users. And so we would love to hear from you all if there's additional metrics that you don't see here when it's online that would be very useful. And I would like to take a short demonstration for this tool right now. I'll walk through a couple different use cases of the tool, and hopefully you can see the applicability of this platform. Okay, so you can see here now I pulled up just to the landing page of the tool. Again, it's still in active development, so we're just giving you a sneak preview, but it will be online on our website very soon. But now it just shows a pop-up explaining a little bit about the tool and how it's used. There will be more documentation once it's available as well. You can dismiss the pop-up, and the first thing you'll notice is that there's a large interactive map, web map window, as well as a series of drop-down selection input fields. And so I'll navigate through those. So first, you'll see that there's a choose equity metric menu item. So you can look through this array of different metrics that we can display and add to the map. And so for the first example here, I'll just showcase the energy burden in the lowest income decile that Ying was talking about earlier in this talk. I select that. I can now choose a definition of disadvantaged community layers, which we've talked about more in previous deep dives, as well as this one. And you can see there's a federal, the CJust or Justice 40 communities layer, as well as state-specific definitions. And in this instance, I'll select the Justice 40 layer. And then we can select from a different scenario. So we've talked a lot about EAU versus net zero. So here I want to select from the US Clean Grid by 2035 scenario. And then we're allowed to select the year. In this case, I'll select from 2030. And you'll see that it's already at the state scale, but for other metrics, there are different inputs that go all the way down to the block scale as well. And then I can select all of the WEC states, which is the current scope of this platform. But as Ying showed in her presentation, that this data set also covers all of the US states. And so I'll select all of these, and then I'll click go. And it'll take a minute to load, but the first thing you'll notice that there's already a button that appears down here that allows you to download the output data. And then as the map is populated, you'll see a couple different things. You'll see a table below showcasing total generation for that year in megawatt hours that we're forecasting, as well as the average energy burden by the state, as well as a plot just showing in a different way that comparing the different state level average energy burdens. You'll see that also overlaid within the map, once it's populated, are the definitions of the disadvantaged community layers. In this case, they are the census tracts showcased by the federal disadvantaged community layer, which is the CJust. And these layers are also included with them are the tribal areas. So you can see different tribal entities and federally recognized tribal lands also identified. This will be more important as I showcase a couple other metrics as well. So I'll come back to that in just a moment. So now I want to go ahead and showcase a different metrics. So I'll press reset, I can navigate again. I'll showcase a little bit of the CO2 emissions, and this time I'll select the California state definition as well as the clean energy, clean grid by 2035, again for 2030. And I'll do it at the county scale and showcase California since we're visualizing the state, their state specific definition of disadvantaged community. You're also allowed to filter down to specific counties if you'd like. It only showcases the counties that have data for that specific layer. So if you don't see a county represented here, it means that there is a NA or 0 value for the specific metric that we're looking at. So we'll click go, it'll run again. It'll take a second to repopulate the figures and the map. And then you'll see the outlines of the layers that we want to showcase. So you'll see the total emissions in metric tons, as well as the total new plants since 2020. We can navigate down to the county scale. We can look at the total annual emissions in metric tons, as well as the overlaying disadvantaged community layers. In this case, it's the California EnviroScreen definition. And also you see the plot has changed below us as well. So you see that it's showcasing the amount of emissions by the specific generator technology. So in this case, gas is the largest emission source, and it's categorized by inside and outside of the DAC census tract that you've selected. So in this case, we're looking at the California EnviroScreen, and it is looking at where the emission points from power plants are and in relation to those census tracts. So we see here that there are a lot more emissions coming from outside of the DAC census tracts in relation to inside DAC census tracts, a much smaller number in this year. And if you'd like, you could also navigate down to the census tract and rerun the same exact metric, and you'll just see a finer scale of the same outputs visualized. So now you can see more up close, also at a smaller scale, a finer spatial resolution of this tool where exactly these are located. And then the last metric I want to showcase briefly is also looking at the change in CO2 emissions from power plants that we're forecasting through our data products. So I'll use the same state and the same counties definition and same county selections. Go ahead and rerun, and now we can see what the change from 2020 baseline year is on the map. So you can see already that there is some negative and positive values. So you'll see here that in the case of Kern County, that there is a large negative change in annual emissions, as well as some positive changes in where exactly the spatial location of changes in CO2 emissions are located. So in addition, there are other metrics and many other outputs that I won't walk through today, but I just hope to demonstrate and hope you all can see the utility of such a tool. Again, we're still looking for feedback, and we welcome your feedback in this case, but we will be publishing this tool onto our project website, and it will again allow you to filter and download the different outputs and metrics associated from this project. So I'll thank you, and I will now bring back the PowerPoint and allow for some question and answer.
Thank you, Stefan. We'll take a few questions for you, and then we'll go to more open Q&A. The first question is regarding changes in the job market caused by decarbonization. Is it possible to visualize change by energy industry type, such as coal or nuclear?
Is that question particular to me or to Milan?
I think on the visualization side, so I think it's for you.
Yeah. So we can visualize job and income changes right now within the scope of different sectors. I think it's the overall utility sector that we currently have results and outputs for. I'm not sure if we can get into the finer. I think there is an extraction and oil and gas specific sector, and Milan can correct me if I'm wrong, but there will be by sector we can visualize changes in jobs.
Millen, did you want to add anything to that?
No, I think Stephen covered the answer correctly. Thanks, Stephen.
Mhm.
The next question for Stefan is, how can industry planners and policymakers use this tool?
Yeah, so I think there are a couple good answers to this, and I think one is just to navigate and filter down the breadth of data products that this project has created down to their specific scale and scenario and year that they're interested in looking at and also downloading. So in that aspect, we can visualize across many different scales, including the state scale, and as well as balancing authority, which is utility service area, which wasn't showcased today, but will be available. But you can look at across different all the different scales, what these outputs look like, and navigate, and then end use cases users can use this to supplement existing data sets and data products to further their research and their policymaking needs. So I think there's a lot of different applications that are available just with all the different scales and products that we have made through this project.
Thanks, Stefan. We have a couple of questions for Millen. The first question is, I was surprised by the level of detail in this presentation, but there were no measures of uncertainty mentioned. Can you describe what these numbers really represent?
Right. So to answer that question, so the numbers are the, so we are doing the DAC projection, and we are also giving some estimate from the implant output. We are calculating uncertainties, and in the previous model, we were just using the machine learning models where we were reporting that what is the probability that the particular census tract or a block group would be a DAC or not. In the current paper, which is under review to a journal, in that paper, we are also presenting what is the confidence level in our predictions for those DAC estimates.
And I think that actually gets to the next question, which I'll read anyway, just in case you want to add anything to it, which was, what is the model accuracy, given that you're doing projections out 2 years? You can probably do a great validation for the model in 2020, and have you done that? And what's the natural noise in the number of jobs from year to year, or 5-year period to 5-year period? So I guess there's 2 questions there.
Thanks, Stephanie, for reading out the question. So we did some validation of the model on the current year. So the DAC Justice 40 data was released somewhere around 2019, 2020. And for those years, we divided the data into 3 sets, training, testing, and validation. And there we validated our model with an accuracy of 85%. Then we took this model and did some validation on the historical data because we were using American survey data set and the loads data set, which is employment statistics starting from 2013 to 2020. And once the models were validated, we went on to do the future projections for 2030 and 2035.
Okay. A question for Ryan. Curious if you'll include geographic variation and cost of living beyond energy costs to complement the variation by income and region.
I'm wondering if maybe that's a question for Ying on the energy burden outcomes.
Oh, yes, that actually may be.
Yeah, so that's a great question. So I'm thinking somewhat our model may capture that, but we do not explicitly model the living cost in terms of the residential energy consumption, whether you have to have a budget and spend some of the budget on food and some of the budget on energy. And when the energy burden is high, you probably have to consume less food and spend more on energy. So that part we don't explicitly model, but we do have the historical GDP across the states, as well as the consumption level of different services in the historical period. So we can somewhat capture that given the historical data. And another point is that GCAM USA or GCAM do have the agriculture and land use module, which has the food model. So in the food demand model, we do have the consumption of food plus the price of the food. So that would give us the expense of the food consumption. So there's no like explicit linkage between food consumption and energy consumption, but that's something I think is very valuable to do in the future.
Thanks, Ying. And now here's a question for Brian. Why are some states projected to have a more unequal distribution than others? Do geographic patterns of inequality change in your projections?
Yeah, they do change somewhat, but this is an area for improvement in the model. Currently, the differences across states are mainly due to differences in the base year. So those general patterns don't change too much from state to state over the time period that we're looking at. One reason for that is that I mentioned the model is driven by the Gini coefficient, projections of the Gini coefficient, which is a summary measure of inequality. So we use that at the national level, projections at the national level, in order to distinguish, okay, this is a scenario in which we're going to have growing inequality. This is a scenario where we're going to have declining inequality. That happens with this Gini coefficient exogenous projection. When we translate to apply that to the state level, since we have a state level model, we're currently applying it equally, its growth rate equally to all states. So that is a step in the model where we could introduce geographic variation in inequality trends. And that would be an interesting thing to do. It would require creating more comprehensive subnational scenarios for the US for thinking about, what's driving inequality differently in different regions of the US, what aspects of the economy, what demographic trends, what else do we want to be representing differentially across states and regions of the country. So that is something that we hope to be able to build on in the future. So right now, the basic geographic pattern doesn't vary too much from what it is now.
Thanks, Brian. And if people have any clarifying questions or follow-ups, please go ahead and put them in the chat as well. The next question is for Stefan. What extensions are possible with the EJVIA tool?
Yeah, there are a lot of extension opportunities. I think it's well suited to adapt to different and new data sets that are available or become available, or even allow different users to upload their own data sets within a certain specified data format. For example, there are different definitions of disadvantaged community layers that could be specific to a large city or municipality that maybe they are interested in overlaying with our data products. There are different scenarios that we might adapt to or might suit the end user better. I think there are a lot of different opportunities to add or augment, enhance additional analyses and spatial overlaps and spatial analyses of the different data products that we've created through the project. And we'd certainly be interested in learning more about what the end user would value as well.
Actually, this is a good time to note that all of our panelists' emails are up on this slide, as is the project website. And I really encourage anybody to reach out directly to any of our panelists for any further questions, or to Natalie Voisin or me. But we do have a few more questions now. One more for Millen. The results were in percentages, but what are the absolute numbers that we're talking about?
So, so these numbers are presented. So the absolute numbers are in terms of the change in the implant output from the current year to the existing year, and they were converted to the percentage by dividing them with the what happened in the current year. So, so for example, the change in job and change in income, those numbers indicate that how much jobs and income, how many jobs would be introduced in each of these sectors under different scenarios, and similarly, what will be the impact on income changes due to those shift in job distributions.
One more for Brian. How was the method tested for downscaling income to the census block level in Washington?
Yeah, so that particular method for the downscaling was tested against the last 3 or 4 years of data at the block level for income distribution. The model was developed on data up to the year 2015, and then it took state level income distribution for 2016 to 2019 and downscaled it to the block level using the estimated model, and then was compared to the block level data over those years. And the results were reasonably good for the model validation.
Thanks, Brian. There's a follow-up question for Millen. Are we asking about the specific absolute value of the numbers? Is it 5 jobs, 500 jobs? What is the range of the numbers of jobs that are being estimated rather than percentage terms?
Right. So this is full-time equivalent of whatever the number of, like, it is the full-time equivalent of the number of jobs. So I can do a quick follow, like an offline follow up on this. I don't remember the exact numbers on those changes, but I can definitely reach out offline and answer this question after this call.
Okay, so you can pull up those numbers, and I can give you the contact information for the person who asked the question. And a question for Ying. How do the scenarios differ in terms of their projected impacts on total residential energy consumption at the state level?
Right. So at the time scale we're measuring, so throughout 2050, all the states have a decrease in residential energy consumption in total. So the decreasing depends on different states. So in the case of Washington state, overall, there's like a 4% to 6% decreases of total residential energy, depending on which income group you're looking at. So in the case of Washington state, D1, the lowest income group, has the largest decrease in residential energy consumption, which is around 6%. But the decrease can go up to 10% for other states, and D1 is not always the group with the largest decrease in energy consumption. Again, this goes back to the spatial variation, depending on both the income growth over time as well as the disparity across the groups. So that causes the difference. Well, in addition to climate and energy prices and state level current energy and emission policies. So we haven't done some sensitivity analysis, but this could be something we can quantify using the model through sensitivity analysis.
Thank you, Ying. And I think this is now the end of the questions that we've gotten so far. But again, please feel free to reach out to any of our panelists directly for any further follow-up questions. Thank you, everybody, and have a great rest of your day.